Okay, so let's unpack this. Today, we're embarking on a deep dive into OEIS sequence A000326. Most people know these as the pentagonal numbers. We've been looking through, well, a stack of fantastic sources, formal papers, discussions online between number theorists, really trying to shortcut you to being well-informed about this really fascinating sequence. So, to start off, pentagonal numbers. They're a type of figure-eight number.
Right. Figure eight numbers you can draw pictures of, essentially.
Exactly. And the nth pentagonal number is defined by this neat little formula, ANN3N12. If you calculate the first few, starting with N0, you get 0, 1, 5, 12, 22, and so on.
Yeah, and what's really fascinating, I think, is how they're constructed. It's this bridge between geometry and arithmetic. Geometrically, you can picture distinct dots.
Okay.
And they're arranged to form the outlines of regular pentagons, but they all share one corner, one vertex.
Ah, I see.
So the third pentagonal number, which is 12, that's 12 distinct dots. And the outermost pentagon has 3 dots making up each side. It gives you a visual.
That helps, yeah. It makes it concrete.
It does. And then arithmetically, you get these same numbers just by summing the first in terms of a, well, simple arithmetic progression. It goes 1, 4, 7, 10.
Uh-oh. So adding 3 each time.
Precisely. Adding 3 each time. And, notice how each term there is 1 modulo 3.
Right.
That's actually a key property. It sort of defines their growth.
That's a great way to see the foundations, the structure. You can really see the visual and the additive parts lining up. But as we were digging through the sources, one thing really jumped out, a connection that feels almost, well, secret. How these numbers connect with prime numbers.
Indeed, yes. And that's not just, a fun fact. It opens up something pretty critical for, say, number theory students. A common question is, well, how do you know? How can you tell if some number x is a pentagonal number?
Right. Is there a test?
There is. A number x is pentagonal if and only if you calculate this.
Yeah.
The square root of 24x plus 1, then add 1 and divide the whole thing by 6.
Okay.
If that result. If it comes out as a natural number, a positive integer.
Then x is pentagonal.
Exactly. It's a direct test. It comes straight from rearranging the original formula.
24. That number seems significant there.
It is. And that ties into the primes. If you take any prime number, that's greater than 3.
Okay, so not 2 or 3.
Right. Any other prime. If you square it and subtract 1, so p squared minus 1, that result, p21, is always divisible by 24.
Always. Wow.
Always. And what's even more remarkable, that multiple of 24. The result of P21, 24. It turns out that number itself is consistently a generalized pentagonal number.
Okay, hold on. Generalized. That sounds like a slight twist. What does generalized mean here?
Good question. So usually we plug in NAA0123 into the formula N3, N12. For generalized pentagonal numbers, we also allow negative integers for n. So n can be 0, plus or minus 1, plus or minus 2, and so on.
Oh, okay. So you get negative results too sometimes.
Exactly. The sequence looks more like 0, 1, then negative 2, then 5, then I have 7, 12. It includes the regular ones, but also these others. And these generalized numbers, positive and negative, they pop up in some really important places in mathematics.
I see.
So this connection between P21 and these generalized pentagonal numbers, it's not just a coincidence. It's structural. It links directly to the fact that primes greater than 3 always have the form 6n plus 1 or 6n1. It shows this deep unity.
That really does put a new perspective on primes, doesn't it? It makes you think how much of this is stumbled upon versus actively sought out. And knowing this, well, it's most valuable when you see how it's used, right? You think of someone like Leonhard Euler.
Absolutely. Euler used these exact numbers.
He didn't just see them as, number patterns. He used them as critical tools.
Right. In his work on integer partitions. Finding all the unique ways you can write a number as a sum of positive integers.
Which sounds simple, but gets incredibly complex.
It does. And pentagonal numbers, particularly the generalized ones, via his pentagonal number theorem, were key to unlocking parts of that puzzle.
It's just a great example of how these seemingly simple sequences can hold such profound mathematical power. So what this really shows us, I think, is that the patterns in pentagonal numbers, while elegant on the surface, hide these deep connections, even to primes. It really makes you wonder, doesn't it? What other elegant mathematical relationships are just hiding in plain sight, waiting for someone to notice?